In this video, we're going to introduce the idea of a random variable. Now, if we think about those two words, and let's start with the word variable. I mean, this is something that is ubiquitous in math and science, where things change in value. So going back to maybe a basic algebra course where you were first introduced to x. And ever since you've had this wonderful relationship with the variable x. It tends to get lost every now and again. That's why you keep having to find x. But yeah, we certainly know the concept of a variable quite well. And randomness. This is something that we're now studying more in depth in this particular course. That's the concept of probability that we're trying to enumerate. This idea of randomness. And what we're going to do now is to put those two ideas together. So all the things that we know how to do with variables, we're going to see how those abilities, right, will enhance what we can know about randomness and probability and so forth. All right, sounds exciting. Well, let's see. Well, let's start by defining what a random variable is, right? And again, I will give you just a verbal description. Other descriptions tend to be very technical, and you're wondering what are they talking about. They use words like measure and sigma algebras and all this stuff. Well, I mean that's on a higher level, but at this level, this is all we need to get going. So a random variable, right, is actually a special kind of function, right? So is a function that assigns a numerical value, to every outcome in a sample space. So every outcome in a sample space, right? So when you think about this, so far our sample spaces, they've been like all over the place, meaning sometimes it's like a very specific event. Other times it's this sort of abstract set, and we don't even really know what the elements are. But now, what this definition is saying is that with every outcome in the sample space, we will be able to associate a number with it, right? And that's what a random variable does, right? So now we're going to start moving to the part of the course where things are going to get very numerical very quickly, right? So not that the idea of a set or anything like that will go away, but now we're adding more of the things that we typically use in a math class, like variables and so forth, right? So there are two types of random variables, right? And if you think back to when we talked about sample spaces, we had said that a sample space can be discrete or it can be continuous. Well, since the random variable is going to associate a numerical value to every outcome in a sample space, then it logically it makes sense that some of your random variables might be discrete if your sample space is discrete, and then the others might be continuous again if your sample space is continuous. So let's make a note of that. A discrete random variable, right, is one based on and what we know about discrete is that it's either a finite set or countably infinite, right? So we've come across those phrases before. So it's one that's based on a finite or countably infinite sample space, right? And these are the random variables that are based on a counting process, right? So that concept doesn't change, right? So the ones that are discrete are typically the ones where you're enumerating something, how much of something, and then you look at all the possibilities of how much of that thing, and then we try to assign probabilities to it, right? So that's where it's all going to come together. So the discrete random variable, these come from a counting process, right? And again, we've seen things like this when we did like our counting techniques and then some of our basic ideas in probability. We just never call them random variables, right? But now we're adding to our vocabulary, right? And similarly, a continuous random variable. So a continuous random variable is one based on a continuous sample space. And continuous sample spaces, they come from processes where you measure something, right? These are based on measurements. So a measurement, or let's just say measuring process, right? And that defines a continuous random variable, right? Another way to think about discrete versus continuous, discrete, when you list these possible like numbers that will be associated with an outcome, there will be gaps between them, right? So it's like a list of numbers where there are gaps between the numbers, right? So a list of numbers, and that list could either be finite or infinite, but it's a list of numbers where there are gaps between the numbers, right? With gaps between them. So with gaps between. As opposed to the continuous, that's an interval where everything is filled in. So it's an interval of numbers with no gaps, right? Now, that interval might be 0 to 1, or 0 to infinity, or negative infinity to a negative infinity. I'm sorry, negative infinity to positive infinity. But those intervals have no gaps, right? So it's an interval of numbers. That's the continuous one with no gaps. So with no gaps, right? And our initial study of random variables will entail the discrete case, right? And for that one, we just need, I can tell you, most of the problems will be algebraic, right? And basic algebra will suffice. But in the countably infinite case, you might end up using infinite series. How fantastic is that going to be, right? Okay, so let's do an example, right? So now I'm defining all these things and introducing all these concepts. Well, what do they really look like? All right, so let's look at a couple examples, and I say we do two examples, and I will make these examples based on experiments that we've done in the past. So I'm not going to, come up with some other fancy type of experiment. I'm just going to take something that we've done, either exactly or close to it, and just show you by changing our perspective and adding a little bit more sophistication to what we're doing, we can now talk about this random variable. All right. So here is the first scenario. So let's say we have 5 men, right, and 4 women. And what we're going to do, the experiment here, is that we're going to randomly choose 3, right? Let's say we're forming a committee where there's no particular role that each person will play. So, it's not like a permutation, it would be a combination. So we're going to choose 3 at random. Right? So out of a total of 9, we're choosing 3. So that's not a new thing. I mean, that's something that we've seen several times over now. But what I'm going to do is I'm going to define a discrete random variable, and what this random variable will count, it will count how many of the 3 are women, right? So let x, now when we define a random variable, the uppercase of that, whatever letter we use, it tends to be uppercase, and that defines the quantity that we're counting. It's almost like when we're defining a set, again, we use the uppercase letter as its name. That's what we're going to do here. So we're going to say let x be defined as the number of women selected or chosen, right? Okay, so that's our count. Well, let's see now what the sample space will be. And now the sample space, when we talk about being represented by a random variable, it's always going to be numeric. So you're not going to have like colors, you're not going to have gender, you're not going to have likes or dislikes. All those almost nebulous things will be somehow coded numerically. And that's what the random variable does. It says, okay, I see the experiment that's going on, but let's make it numerical. What can we count? What can we measure? What are we interested in, right? And in this case, it's the number of women. So here is our sample space. Now, the way the sample space is typically listed when you now define a random variable is you take the lowercase of this letter and you basically state all the possibilities. So I'm going to write sample space, but then I'm going to show you what it looks like when we talk about the sample space in the context of a random variable. So let's look at our sample space here. Right? And it would be all values of x. So we're going to use, and what I'm going to do, I'm going to use my x's, I'm going to make them kind of curved to really distinguish between the uppercase. So the uppercase will be, straight lines that cross. Here I'm just kind of make it curved. In fact, little side story, I used to write my x's like this when I was in high school. This is how we always wrote our x's. It wasn't until college that I started writing x with just the 2 lines that cross. So I'm going to go back to my roots here. Okay, so the sample space, you basically list all the possibilities, all the values that this x could take on, right? So x could be a situation where we have no women chosen. So x could be 0. And then again, this is the idea of listing the numbers now, right? So 0 women, we could have 1 woman, we could have 2 women, and then of course, we can have at most 3, right? So again, here's the definition of a random variable. It tells us what it's counting, and then right below, we're going to list all the possibilities. So now for the sample space, now we could, put it in our set notation. We could wrap these numbers in a set or in braces like we normally do. But a lot of times you'll just see them listed like this, especially in the discrete case when a listing is possible, right? Okay. So that's a random variable. So now we're going to ask ourselves, how likely is it that our random variable is 0? Or how likely is it that our random variable is 1 or 2 or 3? Well, we know these are the four possibilities, right? So now we're going to ask ourselves this question. So how likely, and that's the likelihood question, so how likely is each possible value of x? Each possible value of, well, let me do it like this. State the using the uppercase, all right? Well, we know what we need to figure out when we talk about likelihood. That's probability, right? So I'm going to ask myself this now. What is the probability that my random variable is equal to 0? What is the probability that it will be equal to 1 and 2 and 3? And we'll cover all the possibilities, right? So you'll see a lot of things like this. So we're still going to use our P for probability. So it's the probability that our random variable is equal to 0. Now, in the context of this experiment, that will happen when no women are selected. So what I'm going to write down here is just kind of the almost literal or verbal translation of this. So the probability that the random variable will take on a value of 0 is equivalent to saying no women are chosen. And another way to say that, if you think about it, like the complementary event of this is to say all men, all three chosen are men, right? Well, let's use our combinations now to figure out what this probability is. All right. Now remember, the process is we have 9 individuals, right? So 9 total. And we're choosing 3 out of that 9. So in the denominator, we have to look at all the possible combinations of 9 elements, and we're choosing 3. So that's going to be our 9 choose 3, right? And then to have no women, think of it this way. So we're going to choose 0 out of the 4 women and 3 out of the 5 men. And to combine those two processes, we're going to use our multiplication formula. So it looks like this. So I'm going to have it, since I have it men and women listed that way, so this is where I would choose all 3 out of the 5. And I could even be very specific and say I don't need to put it there, and you'll see why in a second. But then I could say for sure I'm choosing 0 out of the 4, right? And the reason I'm writing this, it's a really nice check that, like when you're setting up your probabilities in terms of combinations, this number and this number must always add up to the 9 here, right? And then the other two numbers must add up to the 3 in the denominator. So this number and this number must add up to this number. That ensures that we are, when we break it in terms of, how many men, how many women, we're always making sure that we're choosing 3, right, out of the 9, right? So we don't somehow switch our numbers around and end up with a different combination than what the question implies. All right. So 5 choose 3. So that is so what I'll do for the first one is write down the factorials, And then in the interest of time, I will skip the factorials, but I'll still give you the numbers as we write down all of these probabilities. So 5 choose 3, 5 factorial over 2 factorial times 3 factorial times, and then 4 choose 0. And this is why this is going to come out to be 1, because we're going to have 4 factorial over 4 factorial times 0 factorial. And 0 factorial is defined to be 1. And then in the denominator, we're going to have 9 factorial over 6 factorial times 3 factorial. All right, so 5 choose 3 is 10. 4 choose 0 is 1. There's only one way you can choose 0 things out of 4 things, and it's by doing nothing, right? And then 9 choose 3, that's 84. So that reduces to, what's that, 5 over 42. All right. So again, let's see what we just computed. We've defined this new variable, and it's random. It's random because it can take on these 4 different values, but there's this level of uncertainty. If the choice that we're making is completely random, then yeah, we don't know beforehand how many women will be selected. So we think about all the possibilities, and now we're trying to enumerate the likelihood of those possibilities. And we've done so for the first case when our probability, or what is the probability that our x is 0. Well, let's continue and do this for the remaining 3 values in our sample space, right? Now, let me see if I can fit them all here. I think I will if I don't write down all the factorials. So the probability that x is equal to 1, and again, I'm not going to write this anymore. I'll say it, but I'm not going to write it down. So the probability that x is equal to 1 means 1 out of the 3 chosen is a woman, and the remaining 2 are men, right? And that probability is going to be 5 choose 2 times 4 choose 1 over 9 choose 3. So the denominator for us is always, again, it's going to be that 9 choose 3. That you could say is our n of s, right? And then over here, for each of these, it will be like a different outcome in our sample space, right? So 5 choose 2, it turns out, is the same as 5 choose 3. And if you kind of think about it, if you think in terms of complements, it makes sense, right? So it's 10, and then 4 choose 1, that's 4. And again, you still have that over 84, right? So that comes out to be, when we reduce it, 10. Yeah, the 4 reduces the 84, so we're going to have 10 over 21, right? So again, notice what we're doing. We're going through and we're computing the likelihood of all the possible values of our variable, right? And keep going. Let's see, what is the probability that x is equal to 2? Well, if x is equal to 2, that means 2 of the 3 chosen are women and 1 is a man. So now that will be 5 choose 1 times 4 choose 2 over the same 9 choose 3. 5 choose 1 is 5. 4 choose 2 is 6. And again, we have the 84. So that one reduces, 6 into 84 is 14. So we have 5 over 14, right? So we've computed the likelihood of 3 of the 4 so far. I think I can squeeze the last one down here. So the probability that x, and again, this is my big X, is equal to 3. So that's where we choose all women and no men. So that's going to be 5 choose 2 times, I'm sorry, 5 choose 0. I was looking at the expression just above. So 5 choose 0 times 4 choose 3 all over, well, let me put the 84 there. All right? So then 5 choose 0, that's 1. 4 choose 3, that's 4. And then over 84, so we get 1 over 21. All right? So let's kind of summarize this in the form of a table, right? Let's do this. So what I'm going to do is I'm going to say, here are the possible values of x. I'm going to write them 0, 1, 2, 3. And then right below, I am going to give the probability for each of these that we just computed. So again, this is why it is, I almost want to say it's a necessity that you get used to writing the random variable as the uppercase letter and the values that it could possibly take on as the corresponding lowercase, right? And so you'll see something like this written quite a bit. So let's list the probabilities. So we got it to be 5 out of 42 for no women. We got it to be 10 out of 21 for one woman. We got it to be 5 out of 14 for 2 women. And then all 3 being women, the likelihood of that occurring is 1 out of 21. And this little table here, it gives us all the information as far as understanding the random nature of this process, this experiment of choosing the 3 women. What I mean by that is, looking at this table, I see all the possibilities, and I see all the corresponding probabilities of those possibilities. That was fun to say. You should try it. And it's such an important and a useful table, right, or idea, is that it has a specific name, and we refer to this. So let me say it this way. So this table, and it can be also referred to as a function. It's just that the function is being given in a tabular way, not like an equation type way, even though we're going to get to that. But this data, this function, right, in this tabular form, is called the probability either mass function or distribution function of the random variable. So this function is called the probability either mass function. I kind of like the mass, and the reason for that will become more apparent later on, but it's either called a probability mass function, abbreviated PMF, or probability distribution. So probability, make sure I spell probability correctly. So probability distribution function, PDF. Right. Now you'll probably hear PDF more frequently than say PMF, but yeah, it's out there, right? So PDF, right? And for a discrete random variable, the PDF is often given in the form of a table, or it might be given like in a more, I don't want to say like y equals f of x form, but that's kind of what in terms of an equation. So you can describe it in a tabular way. You can also describe it in a graphical way, which we will do later on, and also in a algebraic way. right? But this is our random variable, right? Let's do another example. This one will be a little bit easier, just so you can see the variety of experiments that can lead to a random variable. So in this case, we have a fair coin. So a fair coin. And what are we going to do with this fair coin? We're going to toss it 3 times. So toss 3 times. Okay, nothing new there. And we can see, we can definitely identify the random nature of this process. But let's now define our random variable. And since we used x above, x and y tend to go together, and they're all paired up in our xy plane. So let's use y as an example. So uppercase y, we're going to use y to count the number of heads that we observe, right? So y will be the number of heads observed, right? So now let's phrase a question before we do the activity. So this might be the question. Find the probability distribution function of y, right? So that's going to be a very popular type of question. So find the PDF of y. And again, there are 2 things the PDF has to tell us. It has to tell us all the elements in the sample space and convey to us the probability of each associated event, right? So we have to figure out the sample space, which is something that we've been working on. I think we're getting better, if not great, at it. And then we then have to compute probabilities, right, associated with it. Again, something that we're getting better at, soon to be great at. Okay, so the reason I did the 3s because I wanted this sample space to be identical to the previous sample space. So here are the possible values of y. And notice I'm using the lowercase y, right? Well, again, it is possible that you toss this coin 3 times and you observe no heads at all, or 1, or 2, or 3, right? So again, we have a 4-element sample space. But to help us figure out the probabilities, right? The counting techniques are good, but if you have a relatively small sample space, sometimes you can literally list them all, right? So for instance, I'm going to list all the possible outcomes when we toss a fair coin 3 times. We could have tails, tails, tails. Then we could have heads, tails, 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 head, tails, 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 head. Then head, head, tails, head, tails, head, and then tail, heads, heads, and then finally head, head, head. These are the only 8 things that can happen if we toss a fair coin 3 times. So now, let's see, in how many ways can we get 0 heads? Well, this corresponds to just this, right? So this number that's assigned by the random variable is associated with just this one outcome, right? The simple outcome. The ones, so how many ways can I get 1 head? Well, that's these 3. So again, now this isn't just like a simple event. There are different ways that we can end up with the same value for y, right, by having exactly one head. And then the 2, well, how many ways can we get 2 heads? Well, that's the next grouping. So it's these, and then this one as well, right? And then finally, how many ways can we get the just 3 heads? Well, that would be this one, right? So what I wanted to do with this is literally I'm showing you what a random variable does. It takes these kind of arbitrary events in a sample space and it makes numbers out of them, because we can do a lot more with numbers than we can with just these strings of length 3 with letters T and H, right? There's not much we can do with this, but there's a lot we can do with numbers. All right, so now let's write down the probabilities. So let's say, what is the probability that our y is equal to 0? Well, this one is such a small sample space. It has a total of 8 elements, but only 1 out of the 8 would be associated with the number 0. So it's 1/8. What is the probability that y is equal to 1? Well, there are 3 ways, or there are 3, let's say it this way, there are 3 events, or outcomes I should say, in this sample space that would all be associated with the number 1. So again, sample space has size 8. The number of possible outcomes that lead to this value is 3, for a probability of 3/8. And that's also the probability that y is equal to 2. Again, because we have 3 ways of getting 2 heads out of a possible 8 outcomes. So 3 out of 8. And then finally, the probability that y is equal to 3, that's 1 out of 8. Yeah, so sometimes you could see your PDF given like this. It doesn't have to be in the form of a table, but it has to be conveyed to you somehow where it's clear what all the possible outcomes are and what probabilities are associated with them. The table is probably the easiest thing to recognize. So this PDF would look like this. And again, it's the probability that big Y is equal to little y. Again, the big Y is just the name that we're given to the random variable. The little y represents all the possible values that that random variable could take on, right? And then we list our probabilities. So 1/8, 3/8, 3/8, 1/8, right? So that's our PDF. So there, I wanted to do 2 fairly simple PDF constructions based on what we've done before, in terms of one using our counting techniques, the other one where we can literally list the set of possibilities and then count how many satisfy the particular requirement. And then what we will do shortly, define a few more quantities that are associated with a random variable, and then just kind of keep building on it, right? So hopefully I'll see you in the next video for that.